I'm going to go through an explanation of both free response questions from the Unit 5 progress check. So we'll start with the first one, which is a long, I believe, experimental design one. It gives us the block MX at the top of a ramp, block MY at the bottom, MX slides down, collides, and then they move along. And A is asking for the basic physics principles, laws, or equations that students could use to determine graphically the relationship between the release height and the speed of both blocks after they collide and stick together. So there's two things going on here. The first would be conservation of energy, since you're starting with a height and ending at the ground, moving. And the second would be conservation of momentum. So what A was looking for, it was worth 2 points, was conservation of energy and conservation of momentum. Okay, so now moving on to part B. Oh, looks like it's on the next page. Rather, A2. Derive an equation that would relate the initial release height of block X and the final speed of the system using only mx, my, and fundamental constants. So using conservation of energy and conservation of momentum, we're first going to start by saying at the top you have gravitational potential energy, and then when it gets to the bottom of the ramp you're going to have kinetic energy. So mx g hx equals 1/2 mx, this would be bx squared. Mx goes away, so 2g hx square root that will equal vx. Next we're going to go to the conservation of momentum. So it's an inelastic collision since they stick, which means that your mx vx will equal mx plus my, and it wants it in terms of the variable vs. So vx equals the square root of 2g hx, making that substitution. We get mx square root 2g hx over mx plus my will equal vs. Now for part B of this question, it's asking for the real experimental design part. And what it wants us to do is list what we're measuring, symbol for it, and then the equipment using. I've seen this question a few other times on some practice questions, and I think also on one of the actual free response questions from the real test. So it's not unusual to actually have to fill in one of these charts. So what we're looking for, first thing we want to measure would be the mass of both blocks. And symbols, that would be mx and my. And what we want for that is a balance. Next thing we're going to have to measure would be the height, and that would be the release height, hx, and we'll use a meter stick. And then the last thing we need to measure is the final speed, and that would be of both blocks. And that would be the vs. And you can use either a photo gate or a motion detector. I'm just going to go with motion detector. Okay, so an overall procedure we could do in order to measure all of these things. First thing we want to do is mass both blocks using the balance. So I'll write all this out. I'm going to paraphrase the writing out part of this. You should definitely give more detail. Let's move this out of the way. So first, mass blocks using the balance. Next, we want to set up motion detector or photo gate at end of table so that it can get the blocks after they're moving together. Third thing we want to do is measure the release height using the meter stick. 4, hit collect in Logger Pro or whatever data collection system you're using, and release the block. 5, measure the final speed. And last, repeat for 5 different release heights. This part of the question was worth 5 total points. 1 point for listing plausible things to measure with plausible symbols and using plausible equipment. 1 point for saying explicitly that you were going to measure the mass of the blocks. 1 point for saying you were going to be measuring the height. 1 point for somehow indicating you were going to be getting that final speed. And then the final point was for talking about multiple trials or some way to reduce error. So as long as you had some kind of plausible procedure, you need the masses. There's no way around this because if you notice the equation you derived, you need the masses. As long as you have a plausible experiment, then you should be able to get most of the points for this. Okay, now the last part of the question. They repeat the experiment, but this time they replace blocks X and Y with W and Z. And they have their predicted speeds of block Z versus the actual speed. And the question is asking, why does the predicted speed not agree with the actual speed after the collision? The best reason for this is because the collision was not perfectly elastic. Even though the collision was elastic and that they did not stick together and the one continued moving, it's not perfectly elastic. So that means that not all kinetic energy was conserved and some of that kinetic energy could have been lost. Explanations for this: maybe the blocks stuck together for a second before Z moved on. Maybe there was some kind of deformation of the wood with that impact of block W hitting block Z. Maybe there was thermal energy lost. So any of those reasonings, but you would say the collision was not perfectly elastic. Kinetic energy may have been dissipated during the collision, or any other logical reasoning. And this was worth 2 points. 1 point for saying that it was not perfectly elastic, and then 1 point for an appropriate reason for that lack of elasticity. So that was the first free response question. Let's now look at the next one. And here we have the short free response. And this was a paragraph, I believe. So you have the ball thrown towards the ground, direction down, direction back up, and it gives us the grids, wants to know the change in momentum of the ball as a result of the bounce. If there is no change in momentum, then you're going to write no change. And I think the grid's on the next page. Yep. So the horizontal component, there was no change. Why was there no change? Because the mass of the ball didn't change and the horizontal velocity of that ball did not change. Vertically, however, you have the ball coming down and then you have the ball bouncing back up. So the change in momentum, which is also the impulse given to that ball would be in the positive direction. So we want to draw an upward arrow showing a positive vertical change in momentum. And this was only worth 2 points, 1 point for saying no change in horizontal and 1 point for the upward vector for the vertical component. Next part, you have the ball released from height h1 above the ground. After it reaches the ground, bounces, travels to h2. It wants a paragraph length response explaining why, using conservation of momentum and conservation of energy, it does not go as high after the bounce. So this was worth 5 points. There were 4 main ideas they were looking for, in addition to the 1 point for writing a clear, coherent paragraph with logical arguments. I'm going to just outline the 4 main things that they were looking for. I'm not going to write out an entire paragraph, but these are the things that you should include in your answer. So the first point they're looking for is that it was not an elastic collision, and this is because kinetic energy was lost. So by that logic, this was an inelastic collision. We know that because it goes to a shorter height after the bounce, therefore it had to have lost kinetic energy in that bounce. And that's the second thing they're looking for, is the change in kinetic energy. In other words, it's got more kinetic energy before and less after. Because it's got less kinetic energy, you also want to say that the ball lost momentum. The mass stayed the same, the velocity did not, therefore there was a change in momentum where the ball has less momentum after. And then the final thing it's looking for is that some of that energy, some of that initial kinetic energy went somewhere else. In other words, maybe the kinetic energy was lost to thermal energy, but energy left the system somehow. So kinetic energy was dissipated. So what they're looking for is a paragraph where you're addressing these 4 things very clearly. The collision was not elastic because kinetic energy was lost. By definition, an inelastic collision means there is a loss of kinetic energy. Because the ball lost kinetic energy, it had less speed after the bounce, therefore it also had less momentum. The initial kinetic energy going into that bounce was lost to some non-mechanical form, or in other words, it was dissipated. Therefore, there was not as much kinetic energy or speed after the bounce, so it could not reach that final height the same as H1. And then, as AP usually does, 1 point for a clear, consistent, logical, relevant argument that actually addresses the question. One thing to be careful of with these paragraph length responses is that you are addressing everything and exactly what it's asking. This question wanted you to address both conservation of momentum and conservation of energy to explain the answer. So you did need to use both to get the full credit.